For the duration of this reading course, we have focused on three main themes: complex surfaces, thin films, and instabilities studied in these thin films. During this video, we present the derivation of the thin film equation for an arbitrary complex surface, then use this to present the work done by Lin and Kontek on instabilities in thin films. We start with the geometry of the problem. Given a substrate, the surface can be expressed in normal Cartesian coordinates x, y, and z. However, for curved surfaces, this gets very complicated. Thus, we use a curvilinear coordinate system. This involves examining the lines of principal curvature and parameterize these using the variables s1 and s2. This lends itself naturally to the problem, as the principal directions we have chosen are the directions where the curvature of the surface takes its maximum and minimum values, and these are always orthogonal to each other. In this way, we can now write any part of a substrate surface as a function r of s1 and s2. Finally, we choose our last coordinate so that it is perpendicular to s1 and s2. Given our surface and our principal directions, thankfully there are many useful results which we can use. Firstly, we take the derivative of the surface with respect to the curvilinear coordinates s1 and s2. Here we note that the subscript 1 belonging to r refers to the fact that we are taking the derivative with respect to s1, and similarly with s2. Under this notation, we calculate the fundamental forms. These forms hold key properties of the surface, such as the curvature, line element, and so on. The first forms are denoted by EFG and are used to determine the arc length of a curve on a surface, and the second forms are given by LMN. However, given how we initially defined our surface and coordinates, F and M are both equal to 0. Using our fundamental forms, we calculate the basis vectors E1 and E2, which act in the direction of S1 and S2 respectively, and we also calculate N, which is our normal vector. Now we can express any position above our substrate as a function r of S1 and S2 plus S3 of N, where r gives the position on the surface and S3 gives the distance away from the substrate along the normal. Other key quantities are the maximum and minimum curvature, and the scaling factors, where the scaling factor measures the change in position due to a change in the coordinate. Having established our geometry system, we now break down the Navier-Stokes equations to the thin film PDE. For an incompressible flow of fluid density ρ and viscosity μ, the governing equations are the momentum and the continuity equation. We also prescribe 4 boundary conditions. These are the no flux on the substrate, the no slip condition on the substrate, the kinematic boundary condition on the free surface, which indicates that fluid on the surface stays on the surface, and the dynamic boundary condition on the free surface. This consists of 2 components. The normal component gives that pressure jump across the interface is balanced by surface tension. Meanwhile, the tangential component gives the jump in shear stresses across the surface, which for the duration of this reading course we neglect. In this final equation, the letter K denotes the free surface curvature. We observe that the first 2 terms are related to the substrate's curvature, whereas the third term corresponds to the film itself. In our reduction to the thin film PDE, we perform the following steps. We non-dimensionalize the problem, we generate the conservation of flux equation, we examine leading order of the Navier-Stokes, and using the above results and remaining boundary conditions, we generate the thin film PDE. Our choice of scalings for non-dimensionalization is shown below, where we have denoted our typical length scale as L and typical speed as U. It is important to note that we have non-dimensionalized our S3 and U3 with an extra delta parameter. This parameter is quite small and corresponds to the fact that we are dealing with a thin film, so the ratio between our substrate length and film height is small. We also have not decided on how to scale our pressure term yet. Under this non-dimensionalization, we can observe the reduction of the scaling factors, which reduce nicely as shown, where we have written the square roots of E and G as A1 and A2 respectively for ease of notation. When generating the conservation of flux equation, we first rewrite the kinematic boundary condition in terms of U3. We then take our continuity equation and integrate across the film height. Integrating this third term, we just evaluated the limits, which we know via the no flux condition for the substrate surface and the kinematic condition for the free surface. Following these steps, we can rewrite it in the following form, where we choose to write the first integrand as q1, which denotes the fluid flux in the S1 direction, and similarly for Q2 in the S2 direction. Below, we have taken the U1 component of our Navier-Stokes momentum equation, where we have plugged in our non-dimensionalized terms. At this point, we first choose our pressure scaling to match the viscous force. We then write the highlighted terms in their well-known dimensionless form, given by the Reynolds number and Bond number respectively. We now look for terms of leading order. Firstly, we assume that the reduced Reynolds number, as shown, is small. In addition, since we are examining a thin film, we require the aspect ratio delta to also be small. In this regime, the left-hand side is 0, and we are left with a few remaining terms on the right-hand side. We do the same procedure for our U2 and U3 components of the momentum equation, which give us, to leading order, the following three equations. As can be seen, we have kept our delta B term in our leading order balance for the third equation, since B is as of yet undetermined. We start by solving this third equation, integrating over S3 and using the normal component of the dynamic boundary condition. We can easily solve for the pressure. It is important to note that the pressure's dependence on S3 is removed when differentiating with respect to S1 or S2. This makes integrating the other two momentum equations much easier. We then integrate the first momentum equation twice with respect to S3 to solve for U1. In solving for U1, we have used both the no-slip boundary condition as well as the tangential part of the dynamic boundary condition. Having found U1, we can easily calculate the flux Q1. Doing the same thing for U2 and Q2, we can plug both into our conservation of flux equation to generate our final thin film PDE. Examining the components to this PDE, we observe dependence on the curvature, which considers both the substrates and film's curvature, gravity in the normal direction, and gravity in the tangential condition as well. Having derived the thin film PDE for an arbitrary surface, we now examine the work done by Lin and Klondike on instabilities in thin films. During a series of 3 papers, they studied 2D and 3D flow for an inverted plane, as well as a funnel. We look at the planar case, breaking down our thin film equation for this geometry. Since it is a plane, we pick our coordinates to be the standard x, y, and z. This results in our different scaling factors all just being 1, which in turn simplifies our surface operators. Furthermore, our different substrate curvatures are both equal to 0, which results in our free surface curvature being only dependent on the film itself. In this coordinate system, our PDE breaks down as follows. Under the scaling of the velocity, as well as their choice of typical length scale, we are back to their equation, which is dependent on a single parameter d. This is dependent on the capillary number and angle, and is positive for fluid flowing on the plane and negative for flow down an inverted plane. Over the course of their papers, they studied how variations in d led to different wave-like behavior. In their first paper, they examined the two-dimensional case. In the case of h independent of y, we are left with the following PDE. To close out the problem, they choose the following boundary conditions. The height of the film at x equals 0 is always equal to 1, and setting the highlighted term equal to 0 results in the flux in the x direction being equal to 1, so there's a constant flux on the left-hand side. In the model, they have made use of a precursor, a very thin layer of wetness on the surface. This is done to avoid the immense complication of having to calculate the contact angle between the thin film and the surface repeatedly. Under this model, they showed 3 different regimes for the parameter d. We examined the evolution for increased magnitude of d. Looking at our first regime, examining how it evolves with time, we observe a large capillary ridge at the front. Behind this, we notice strong damping. In this regime, there's a traveling wave solution, where it can be found that the speed u is 1 plus b squared, where b is the precursor height. For our second regime, at d equals minus 1.5, we observe 2 different types of waves. These waves move faster than the front itself, and so we notice spikes in amplitude when the wave catches up with the ridge and merges. Our next 2 figures are both under the third regime. For d equals minus 2, the waves have a more sinusoidal behavior. As the magnitude increases, the wave-like behavior changes to look more like an excited pulse, as shown in d equals minus 2.5. As can be observed, a base state only exists for d greater than minus 1.1. Moving on, we present the linear stability analysis carried out for this regime. We look at the thin film found in regime 1. Given our initial PDE, we assume that the thin film height, h of x of t, takes the form of 1 plus psi of x of t, where psi is very small. Plugging in this form of h to the leading order in psi, we are left with the following PDE. We write psi equals the exponential of I times kx minus omega t, where omega has both a real and imaginary part. Simplifying the results, we are left with the following dispersion relations. We are interested in omega I. For omega I negative, the real component is negative, and so any perturbation will decay to zero. But for positive omega I, they will grow. For negative d, we find that they are unstable for large wavelengths. A critical wave number k is given by the square root of minus d, and the most unstable wave number is given by the square root of minus d over 2. Thus, Lin and Connick found that for positive d, the thin film is stable under perturbations, but for negative d is unstable for sufficiently large wavelengths. Having already found the traveling wave solution for the xz case, they consider a moving frame defined by s equals x minus vt for the 3D flow. They write this solution as little h equals big H plus epsilon h1, where big H is the traveling wave solution, and epsilon is much less than 1. Plugging into the master equation for 3D flow, the leading order term in epsilon gives the 2D traveling wave equation, whereas to first order in epsilon, they acquire an equation to describe h1. They express h1 as a superposition of Fourier modes, where for each q there is an eigenvalue problem, where they identify the eigenvalue which corresponds to the largest growth rate. The results are shown below. Of primary interest are the blue and black curves, which correspond to negative d. As d increases in magnitude, the range of unstable wave number steadily increases. This in turn corresponds to smaller wavelengths being unstable. The results of the single mode perturbations are shown for d equals minus 1 for the transverse case. In these plots, the transverse length is equal to the wavelength. As wavelength grows, more fingers end up appearing. Finally, in their paper on the funnel, there were 3 main steps. They initially examined a self-similarity solution. Under short enough distances, they find that flow is identical to that down an inclined plane. They then perform their linear stability analysis via a snapshot in time when the film has reached a set position. Here they take the angle of incline and the thickness of the film at the inflection point behind the ridge. They then match it to the suitable traveling wave on an inclined plane with the same characteristics. In the figure below, we see the film profile for the funnel in blue and the incline in black. We observe the matched inflection point behind the ridge. By matching the film profiles in this way, they are still able to obtain the most unstable wave number, which does end up agreeing with the experiment. To conclude, we briefly look at the results of Hubert and Takagi for golden syrup down a beach ball. They were able to find the solution for the height evolution, which agreed before instabilities occurred. However, these instabilities were not studied. An open question that remains is whether it is possible to adapt the linear stability analysis performed by Connick and Lin to different geometries such as the beach ball, and under what conditions this can be done. Given the curvature of the ball and the changing components of gravity, are there base states that exist, and if so, for how far down the ball do they exist?